My name is Harsh Gandhi and I am pursuing PhD in Civil and Environmental Engineering at UMass Lowell. Today I am presenting the impact of soil profile and the bridge span length on the design of steel piles in integral abutment bridges under thermal loading. IABs are the one without the expansion joint in compare with the conventional bridges. In conventional bridges, expansion joints are used to counteract the change in bridge length due to the temperature. However, the construction and the maintenance of those expansion joints are costly, and to solve these problems, states and municipalities are preferring integral bridges over regular bridges. But in contrast, the designing of integral abutment bridges are challenging due to the temperature effect. This is due to the IAB have the continuous deck integral with the abutment walls, and the walls are connected with the piles either in pin or a fixed connection. Hence, designing of the piles are in a direct connection with the pile head displacement, and those pile head displacement depends on the span length of the bridges, temperature difference, abutment stiffness, and so on. In this study, we focused on the effect of span length and the abutment stiffness by varying the soil profile behind it on the designing of the steel piles in integral abutment bridges under thermal expansion. Important criteria in a pile designing are fixity point and the bending moments at the pile head and at the second segment. So fixity point is where lateral displacement will become 0 or less than 0.01 feet, where the bending moments in a pile are also important aspect of the pile designing to decide the occurrence of plastic hinge in top and in the second segment. To analyze the impact of span length and the soil behind the abutment wall, 3D finite element model was used. 4 cases were studied by varying the span length from 150 feet to 275 feet and the soil behind the wall from loose soil to the dense soil. During the analysis, the thermal loading, soil around the pile, and the cross-sectional properties of the steel piles were kept constant. By doing so, larger pile head displacement happened due to the larger span length, in contrast with smaller pile head displacement due to the smaller span. Here in pile modeling result, figure 3 represent the pile displacement along the length of the steel piles oriented in a weak axis. The results are in a good agreement with the assumed hypothesis. Here, in a pile head displacement of 275 feet span is higher than 150 feet span, and as a result, effective length of fixity point is more for 275 feet span in compared with the 150 feet span. In zoomed in image, we can clearly confirm that the fixity point for 150 feet span bridge reached 0.25 feet earlier than 275 feet span. Figure 4 represents the bending moment along the steel pile length oriented in a weak axis with the dense soil behind the abutment wall. The moment results are also in a good agreement with the assumed hypothesis, as moment in a top and the second segment of 275 feet span is higher than the 150 feet span. This moment analysis was also important in a pile designing, as occurrence of plastic hinge in any of these segment can cause the plastic failure. Here, figure 5 similarly represent the deflection and the moment profile of the steel pile with the loose soil behind the wall. Loose soil behind the wall have behaved similarly as assumed hypothesis. However, due to the less stiffness of the abutment, pile head displacement values and the moment values will be higher in compare with the dense soil behind the abutment wall. Now the golden question is, which soil behind the abutment wall is better, dense or loose? Now looking at the table 1, for the qualitative analysis, we can clearly see that with the increment of the span length, the effective length of the fixity point will only increase by 0.25 feet. However, for the individual span, the same effective length will increase by 0.55 feet. Hence, for the fixed point criteria, dense soil behind the wall is better, as the stiffness of wall will be higher due to the dense soil, and the less pile held displacement will occur, results in reaching the fixed point early. Similarly, for the moment part of design criteria, the increment in a span length will increase the moment at the top segment by 10% and at the second segment by 2% only. But for the individual span length, the same moment will increase 61% in a top segment and a 65% in a second segment. Hence, there is a higher chance of having a plastic hinge into loose soil behind the abutment wall scenario due to the same reason of less flexibility due to the soil, which lead higher pile head displacement and a moments overall. In a nutshell, increment in a span length will increase the pile head displacement, moments, and the effective length of the fixed point. And for the dense soil behind the abutment wall, that will increase the stiffness of the wall, that will lead to the less pile head displacement, less moments, and the effective length of the fixed point would also be reduced. Thank you so much for listening.